Welcome to this comprehensive guide on the secant function. The secant function is one of the 6 fundamental trigonometric functions, and today we'll explore what it is, how it works, and how to use it in practical calculations. The secant function, written as sec of x, is defined as 1 divided by cosine of x. In other words, secant is the reciprocal of the cosine function. This means that wherever cosine has a value, secant will have the value 1 divided by that cosine value. In a right triangle, we can also define secant geometrically. For any angle theta in a right triangle, secant of theta equals the length of the hypotenuse divided by the length of the adjacent side. This gives us our triangle definition. Secant of theta equals hypotenuse over adjacent. This is equivalent to our reciprocal definition since cosine of theta equals adjacent over hypotenuse. Now let's work through our first example. We want to find the secant of 60 degrees using our reciprocal definition. Remember, secant equals 1 divided by cosine. Step 1, we write secant of 60 degrees as 1 divided by cosine of 60 degrees. Step 2, we recall that cosine of 60 degrees equals 1/2. This is a standard trigonometric value you should memorize. Step 3, we substitute 1/2 for cosine of 60 degrees. 1 divided by 1/2 equals 2. Therefore, secant of 60 degrees equals 2. For our second example, we have a 3, 4, 5 right triangle. We want to find the secant of angle theta, which is the angle opposite the side of length 3. Step 1, we use our triangle definition. Secant of theta equals hypotenuse over adjacent. Step 2, the hypotenuse is 5, and the adjacent side to angle theta is 4. Therefore, secant of theta equals 5 over 4. Step 3, converting to decimal form, 5 divided by 4 equals 1.25. So secant of theta equals 1.25. For our third example, we're given that cosine of x equals 3 over 5, and we need to find secant of x. This demonstrates the reciprocal relationship directly. Step 1, we start with our fundamental definition. Secant of x equals 1 divided by cosine of x. Step 2, we substitute the given value. Cosine of x equals 3 over 5, so secant of x equals 1 divided by 3 over 5. Step 3, to divide by a fraction, we multiply by its reciprocal. 1 divided by 3 over 5 equals 1 times 5 over 3, which equals 5 over 3. In this introduction to the secant function, we've learned 3 key concepts. First, secant is the reciprocal of cosine. Second, in right triangles, secant equals hypotenuse over adjacent. Third, secant values are always greater than or equal to 1, or less than or equal to -1. In the next sections, we'll explore the properties, graphing, and applications of the secant function in much greater detail. Now that we understand what the secant function is, let's explore its fundamental concepts and properties. These key ideas will help you work with secant in any mathematical context. The most important concept is the definition of secant. Secant of x equals 1 divided by cosine of x. This means secant is simply the reciprocal of the cosine function. This reciprocal relationship is crucial. Wherever cosine has a value, secant will be 1 divided by that value. For example, if cosine equals 1/2, then secant equals 2. In a right triangle, secant has a geometric meaning. Secant of an angle equals the hypotenuse divided by the adjacent side. This gives us a visual way to understand secant. So in this right triangle, secant of theta equals hypotenuse divided by adjacent. This is the geometric interpretation of the secant function. Now let's discuss the domain of the secant function. The domain includes all real numbers except where cosine equals 0. This happens at x equals pi over 2, 3 pi over 2, 5 pi over 2, and so on. These are the values where cosine equals 0, which makes secant undefined since we cannot divide by 0. For example, at x equals pi over 2, 3 pi over 2, and -pi over 2. The range of secant is also important to understand. Secant can take any value less than or equal to -1 or greater than or equal to +1. It never takes values between -1 and +1. This makes sense because secant equals 1 over cosine. And since cosine is always between -1 and +1, secant must be at least 1 in absolute value. Secant is a periodic function with period 2 pi. This means that secant of x plus 2 pi equals secant of x for any value of x. The function repeats its pattern every 2 pi units. Secant is also an even function. This means that secant of -x equals secant of x. The graph of secant is symmetric about the y-axis, just like cosine. Finally, secant has vertical asymptotes. These occur at the same x values where secant is undefined, where cosine equals 0. At these points, the secant function approaches positive or negative infinity. These fundamental properties, the reciprocal definition, domain restrictions, range limitations, periodicity, even function behavior, and vertical asymptotes, form the foundation for understanding how secant behaves in all mathematical contexts. Now we'll learn how to graph the secant function step by step. The key to understanding the secant graph is recognizing its relationship with the cosine function. Step 1. We start by graphing the cosine function. This blue curve shows y equals cosine x, which oscillates between -1 and +1 with a period of 2 pi. Step 2. We identify where cosine equals 0. These red dots show the points where cosine is 0. At these x values, secant will have vertical asymptotes because secant equals 1 divided by cosine. Step 3. We graph the secant function. Since secant equals 1 divided by cosine, wherever cosine has a maximum value of 1, secant also equals 1. Wherever cosine has a minimum value of -1, secant also equals -1. Notice these key connection points. Where cosine reaches its maximum of 1, secant also equals 1. Where cosine reaches its minimum of -1, secant also equals -1. These are the only points where the two functions intersect. The secant function creates characteristic U-shaped curves between each pair of asymptotes. Where cosine is positive and decreasing toward 0, secant increases toward positive infinity. Where cosine is negative and increasing toward 0, secant decreases toward negative infinity. The domain of secant includes all real numbers except where cosine equals 0. The range of secant is -infinity to -1, union 1 to positive infinity. Notice that secant can never have values between -1 and +1. This complete graph shows the secant function with its vertical asymptotes, U-shaped branches, and periodic behavior. The period is 2 pi, just like cosine. Understanding this relationship between cosine and secant makes graphing secant much more manageable. Now we'll explore the essential properties and identities of the secant function. These mathematical relationships are fundamental tools for solving equations and simplifying expressions involving secant. The most fundamental property of secant is the reciprocal identity. Since secant is defined as the reciprocal of cosine, we have secant of x equals 1 divided by cosine of x. This identity tells us that wherever cosine is 0, secant becomes undefined, creating vertical asymptotes. And wherever cosine has maximum or minimum values, secant will have corresponding minimum values. The second crucial identity is the Pythagorean identity for secant. This states that tangent squared of x plus equals secant squared of x. This relationship comes from the fundamental Pythagorean theorem applied to trigonometric functions. We can derive this identity from the basic Pythagorean theorem. Starting with sine squared plus cosine squared equals 1, we divide both sides by cosine squared to get this powerful relationship. In calculus, secant has specific derivative and integral formulas. The derivative of secant x is secant x times tangent x. The integral is more complex, involving the natural logarithm of the absolute value of secant x plus tangent x. Let's work through our first example. We need to find the value of secant of 60 degrees using the reciprocal identity. This will demonstrate how to convert between secant and cosine. We start by applying the reciprocal identity. Secant of 60 degrees equals 1 divided by cosine of 60 degrees. From our knowledge of special angles, we know that cosine of 60 degrees equals 1/2. Substituting this value, we get secant of 60 degrees equals 1 divided by 1/2, which simplifies to 2. For our second example, we'll use the Pythagorean identity to simplify an expression. Given that tangent of theta equals 3, we need to find secant squared of theta. We'll use the Pythagorean identity. Tangent squared of theta plus 1 equals secant squared of theta. Since tangent of theta equals 3, we substitute this value into our identity. Tangent squared of theta becomes 3 squared, which equals 9. Now we can calculate secant squared of theta. 9 plus 1 equals 10. Therefore, secant squared of theta equals 10. Our final example involves calculus. We need to find the derivative of the function f of x equals x times secant of x. This requires the product rule combined with our knowledge of secant's derivative. Since we have a product of two functions, we'll use the product rule. The derivative of u times v equals u prime times v plus u times v prime. Let u equal x and v equals secant of x, then u prime equals 1 and v prime equals secant of x times tangent of x. Applying the product rule, f prime of x equals 1 times secant of x plus x times secant of x times tangent of x. This simplifies to secant of x plus x secant of x tangent of x. These properties and identities of secant are essential tools in trigonometry and calculus. The reciprocal identity connects secant to cosine, the Pythagorean identity relates secant to tangent, and the calculus formulas enable us to work with secant in advanced mathematical contexts. Now we'll learn how to solve equations that involve the secant function. This is a systematic process that uses the reciprocal relationship between secant and cosine. The general method for solving secant equations follows three clear steps. First, we isolate the secant function on one side of the equation. Second, we convert the secant to cosine using the reciprocal identity. Since secant equals 1 over cosine, we can rewrite our equation in terms of cosine. Third, we solve for x using the inverse cosine function, being careful to find all solutions within the appropriate interval. There are important restrictions to remember. The secant function has domain restrictions where cosine equals 0. We must also consider the periodic nature of secant, and remember that the absolute value of secant is always greater than or equal to 1. Let's start with our first example. We need to solve the equation secant of x equals 2. Here's our equation. The secant of x equals 2. Notice that 2 is greater than 1, so this equation has solutions. Step 1 is already complete, because secant of x is isolated on the left side of our equation. Step 2, we convert secant to cosine. Since secant of x equals 1 over cosine of x, our equation becomes 1 over cosine of x equals 2. Taking the reciprocal of both sides, we get cosine of x equals 1/2. Step 3, we find all solutions. Cosine equals 1/2 when x equals pi over 3 or negative pi over 3 plus any multiple of 2 pi. These are our complete solutions for the first example. The k represents any integer, giving us infinitely many solutions due to the periodic nature of the secant function. Our second example is more complex. We need to solve secant of 2x equals -2. Here's our equation. Notice that we have 2x inside the secant function, and the right side is -2. Step 1 is complete, since secant of 2x is already isolated. Step 2, converting to cosine, we get 1 over cosine of 2x equals -2. Taking the reciprocal of both sides, cosine of 2x equals -1/2. Cosine equals -1/2 when the angle is 2 pi over 3 or 4 pi over 3 plus multiples of 2 pi. So 2x equals these values. Dividing both sides by 2, we get x equals pi over 3 plus pi k, or x equals 2 pi over 3 plus pi k. Notice that our period is now pi instead of 2 pi because of the coefficient 2 in front of x. Our third example is a quadratic equation in secant. We need to solve secant squared of x minus 3 secant of x plus 2 equals 0. This is a quadratic equation where secant of x is our variable. We can solve this by factoring or substitution. Let's use substitution. Let u equal secant of x. Then our equation becomes u squared minus 3u plus 2 equals 0. This quadratic factors as u minus 1 times u minus 2 equals 0. So u equals 1 or u equals 2. Substituting back, we get secant of x equals 1 or secant of x equals 2. For case 1, secant of x equals 1 means cosine of x equals 1, so x equals 2 pi k. For case 2, secant of x equals 2 means cosine of x equals 1/2, giving us x equals plus or minus pi over 3 plus 2 pi k. Our complete solution includes all three families of solutions. X equals 2 pi k, pi over 3 plus 2 pi k, and negative pi over 3 plus 2 pi k. To summarize, when solving secant equations, always verify that the absolute value of secant is at least 1. Convert to cosine using the reciprocal identity. Remember to find all solutions using the periodic nature of the function. For quadratic equations in secant, substitution and factoring are powerful techniques. Now we'll explore how to transform the secant function using the general form. Understanding these transformations allows you to manipulate and analyze secant functions in various mathematical contexts. The general form of a transformed secant function is y equals a times secant of the quantity bx plus c plus d. Each parameter controls a specific type of transformation. Parameter a controls vertical stretch, compression, and reflection. When a is greater than 1, the graph stretches vertically. When a is between 0 and 1, it compresses. When a is negative, the graph reflects across the x-axis. Parameter b affects the period of the function. The new period becomes 2 pi divided by the absolute value of b. When b is greater than 1, the period decreases, making the function repeat more frequently. Parameter c creates a horizontal shift. This shift also affects the location of vertical asymptotes, moving them left or right along the x-axis. Parameter d produces a vertical shift, moving the entire graph up or down without changing its shape or period. Now let's work through 3 examples to see these transformations in action, starting with a simple vertical stretch. Example 1, graph the function y equals 2 secant of x. Here we have a equals 2, b equals 1, c equals 0, and d equals 0. Since a equals 2, this function will be vertically stretched by a factor of 2 compared to the basic secant function. First, let's set up our coordinate system and draw the vertical asymptotes. These occur where cosine equals 0, at x equals negative 3 pi over 2, negative pi over 2, pi over 2, and 3 pi over 2. The gray dashed curve shows the original secant function for comparison. Notice how each point on the original function has a y-coordinate between negative 1 and 1, or greater than 1 and less than negative 1. Now the blue curve shows our transformed function y equals 2 secant x. Every y-coordinate is multiplied by 2, so the minimum values are now at positive and negative 2 instead of positive and negative 1. At x equals 0, the original secant equals 1, but our transformed function equals 2. At x equals pi, the original secant equals negative 1, but our transformed function equals negative 2. This completes our first example. The vertical stretch transformation multiplies all y values by the factor a. Now let's move to a more complex example involving period changes. Example 2. Graph the function y equals secant of the quantity 2x minus pi over 2. We need to identify our parameters by rewriting this in standard form. First, let's factor out the coefficient of x. We can rewrite 2x minus pi over 2 as 2 times the quantity x minus pi over 4. Now we can identify our parameters. A equals 1, b equals 2, c equals negative pi over 2, and d equals 0. The period is 2 pi divided by the absolute value of b, which equals 2 pi divided by 2, giving us a period of pi. This is half the normal period. The horizontal shift is pi over 4 units to the right, which will move all asymptotes and key points in that direction. The new asymptotes occur where 2x minus pi over 2 equals odd multiples of pi over 2. This gives us asymptotes at x equals negative pi over 4, 3 pi over 4, and 5 pi over 4. Here's our transformed secant function. Notice how it completes a full cycle in just pi units instead of 2 pi, and everything is shifted pi over 4 units to the right. This example shows how b affects the period and c creates horizontal shifts. Our final example will combine multiple transformations. Example 3. Graph the function y equals negative 1/2 secant of the quantity x over 2 plus pi over 4 plus 3. This function uses all 4 transformation parameters. Here a equals negative 1/2, b equals 1/2, c equals pi over 4, and d equals 3. Each parameter creates a different transformation. A equals negative 1/2 creates vertical compression by 1/2 and reflection across the x-axis. B equals 1/2 gives us a period of 4 pi. C equals pi over 4 shifts the graph pi over 2 units left. D equals 3 shifts everything 3 units up. The asymptotes occur where x over 2 plus pi over 4 equals odd multiples of pi over 2. This gives us asymptotes at x equals negative 3 pi over 2, negative pi over 2, pi over 2, and so on. The dashed horizontal line at y equals 3 shows our new center line due to the vertical shift. Here's our final transformed function. Notice the inverted U-shapes due to the reflection, the compressed amplitude, the stretched period, and how everything is centered around y equals 3. At x equals 0, the function value is 2.5, which is 3 minus 0.5. At x equals 2 pi, the function value is 3.5, which is 3 plus 0.5. These show the compressed and shifted range. This example demonstrates how multiple transformations work together. The order of operations in the function determines how each transformation affects the final graph. Understanding these patterns helps you analyze any transformed secant function systematically. The secant function isn't just an abstract mathematical concept. It has powerful real-world applications across many fields, including physics, engineering, architecture, astronomy, and computer science. We'll explore 3 detailed examples that demonstrate how secant helps solve real problems in these fields. Each example will show you the practical value of this trigonometric function. Our first example comes from mechanical engineering. Engineers often need to analyze forces acting at angles, and the secant function helps calculate the total force magnitude. Here's our problem. A cable supports a 500 Newton load at a 30-degree angle from vertical. We need to find the tension force in the cable. Let me draw a force diagram. The vertical line represents the 500 Newton load, and the blue line represents the cable at 30 degrees from vertical. We need to find the tension T. Now let's solve this step by step. The key insight is that the vertical component of the tension must equal the load. Step 1. The vertical component of tension equals the load. So T times cosine of 30 degrees equals 500 newtons. Step 2. To solve for T, we divide both sides by cosine of 30 degrees. Step 3. Since 1 over cosine equals secant, we can write this as 500 times secant of 30 degrees. Step 4. Secant of 30 degrees equals 2 over square root of 3. So T equals 500 times 2 over square root of 3, which gives us approximately 577.4 newtons. The tension in the cable is 577.4 newtons. This is greater than the load because the cable is at an angle, requiring more force to support the same vertical load. Our second example comes from architecture. When designing sloped roofs, architects use secant to calculate the actual length of roof beams. Here's the problem. A roof beam spans horizontally 8 meters and rises at a 25-degree angle. We need to find the actual length of the roof beam. Here's our roof diagram. The horizontal span is 8 meters, the beam rises at 25 degrees, and we need to find the length L of the actual beam. The horizontal distance is the adjacent side, and the beam length is the hypotenuse. This is a perfect application for secant. Step 1. Cosine of 25 degrees equals the adjacent side over the hypotenuse, which is 8 over L. Step 2. Solving for L, we get L equals 8 divided by cosine of 25 degrees. Step 3. This is equivalent to 8 times secant of 25 degrees. Step 4. Secant of 25 degrees is approximately 1.13, so L equals 8 times 1.103, which gives us 8.83 meters. The roof beam must be 8.83 meters long. This is longer than the horizontal span because of the slope, and secant gives us the exact multiplier needed. Our final example comes from astronomy and satellite communications. When a satellite is at an angle from vertical, we need secant to calculate the actual signal distance. Here's our astronomy problem. A communication satellite is 400 kilometers above Earth. The signal travels at 15 degrees from vertical. We need to find the signal path length. Here's our satellite communication setup. The satellite is 400 kilometers directly above Earth, and the signal travels at 15 degrees from vertical to reach a ground station. The vertical distance is 400 kilometers, and we need the hypotenuse length. This is another perfect secant application. Step 1. Cosine of 15 degrees equals the adjacent side, 400 kilometers, over the hypotenuse d. Step 2. Solving for d, we get 400 divided by cosine of 15 degrees, which equals 400 times secant of 15 degrees. Step 3. Secant of 15 degrees is approximately 1.035, so d equals 400 times 1.035, giving us 414.2 kilometers. The signal must travel 414.2 kilometers to reach the ground station. Even a small 15-degree angle increases the distance by over 14 kilometers, which affects signal strength and timing. The secant function proves invaluable across multiple disciplines. In engineering, it helps analyze forces and design structures. In architecture, it calculates material lengths for angled construction. In astronomy, it determines signal paths and celestial positions. In physics, it models waves and oscillations. And in computer science, it optimizes algorithms and analyzes data patterns. These examples demonstrate that secant isn't just theoretical mathematics. It's a practical tool that helps solve real problems in science, technology, and engineering. Understanding secant gives you the power to tackle complex calculations in many professional fields. Now that we've explored the secant function in detail, it's important to understand why this function matters in mathematics and how it developed throughout history. While sine, cosine, and tangent are sufficient for solving basic right triangles, the secant function, along with cosecant and cotangent, provides mathematical completeness. These 6 trigonometric functions form a complete set that is closed under reciprocals. The secant function becomes particularly valuable in calculus and integral calculus. It frequently appears as an antiderivative in integration problems. For example, the integral of secant x appears in many calculus problems and has the elegant solution, the natural logarithm of the absolute value of secant x plus tangent x. Secant functions are also essential in cartography, particularly in Mercator projections used for world maps. This projection preserves angles and shapes locally, making it invaluable for navigation. Now, let's explore the fascinating history behind the secant function and how it got its name. The term secant comes from the Latin word secare, which means to cut. This name originated from its use in circle geometry, where a secant line cuts through a circle at 2 points. The development of trigonometric concepts, including what we now call the secant function, involved contributions from ancient civilizations. The Greeks made significant advances in geometry and trigonometry, while ancient Indian mathematicians developed sophisticated trigonometric tables and methods. As we conclude our comprehensive exploration of the secant function, let's recap the key insights we've discovered. We've learned that secant is the reciprocal of cosine, making it essential for mathematical completeness. It's valuable in calculus and integration, has important real-world applications like Mercator projections, and has a rich historical development spanning ancient civilizations. Thank you for joining me on this mathematical journey through the secant function. If you found this video helpful, please give it a like and subscribe for more educational content. Feel free to leave questions or suggestions for future topics in the comments below. Keep exploring the beautiful world of mathematics.